For my final project, I'll discuss the empirical modeling of magnesium cation complexes. For a little background on the system at play, the divalent magnesium cation is a member of a group of metal cations including calcium, potassium, and sodium, which are readily found in and crucial to many processes of biological systems. Interactions of both the cation and the hydrated magnesium cation play critical roles. The hydrated complex is present anytime the cation is found in an aqueous solution, generally consisting of 6 water coordinated to magnesium in an inner shell. Magnesium's ability to polarize other molecules give it a role in many processes. These include the stabilization of anions and relieving of electrostatic repulsion, allowing otherwise unfavorable interactions to occur. Generally, using neutral ligands, these complexes take the form of magnesium bound to N ligands with an overall 2+ charge. Depending on the ligand, this charge can become increasingly distributed throughout the entire complex through charge exchange. Typically, this complex exists with coordination of 6 and a roughly octahedral geometry. Coordination bonding involves dative covalent bonds, where both binding electrons come from the ligand. Thus, ligands with 2 free electrons, typically in the form of a lone pair, are common. For this study, water, methanol, and formamide are examined. These are small enough to be studied easily, while still being relevant functional groups found on larger molecules. The motivating questions of this project include, first, how do these 3 ligands compete in binding? The expectation here is that the more polarizable formamide and methanol will bind more strongly for initial ligands, while at increased coordination, water will become more favorable. This is based on the results of previous studies. The second and third questions revolve around an empirical expression developed for predicting the total binding energy of mixed ligand complexes. First is, does this empirical expression remain accurate at different levels of theory? And second, does it remain accurate for complexes it was not directly fit on? Essentially, we're asking, are the applied weightings universal or local to the results of the original author? The expectation here is that the model will hold up fairly well at different levels of theory, but likely be less accurate than the one it was fit on. To best compare against previous work, each structure was optimized at the B3LYP level using a 631G basis set with diffuse and polarization functions. Thermodynamic data using this theory had been found to relate to experimental data fairly well in previous studies. In addition, a double hybrid functional, a range-separated hybrid, and a couple clustered method were employed. The double hybrid uses a fraction of an MP2 calculation in addition to the standard hybrid DFT method. The range-separate hybrid makes use of increased exact exchange at long distances to make up for generally poor DFT performance at these distances. The coupled clustered method was employed as a particularly accurate point of comparison based on its performance against benchmark sets for similar systems. Each of these are expected to account for interactions B3LYP generally fails to, like long-range ligand-ligand interactions, and a more accurate representation of charge transfer. Moving to the results for single ligand-type complexes, water was examined first. As expected, binding energies decrease with each subsequent water ligand. In a similar fashion, the average magnesium-oxygen bond length increases by roughly 0.15 angstroms. In comparing methods, for the first water, there is good agreement for all but the range-separated method, which predicts a slightly lower binding. As coordination increases, the coupled clustered calculations estimate greater bindings than any other, with the double hybrid and range-separated hybrid more closely agreeing than the B3LYP method. Looking at methanol, very similar trends are apparent. The magnesium-oxygen distance increases by 0.22 angstroms. Compared to water, the double hybrid method is more closely related to the coupled cluster results. Additionally, at n equals 5 and 6, adding an additional methanol ligand binds with almost identical strengths. Finally, formamide behaves very alike to methanol. The magnesium-oxygen distance increases by 0.34 angstroms, and thus the initial formamide ligand binds more tightly than either other option. However, the addition of the 6th ligand is the weakest of any by far. Notably, there is better agreement between all 4 methods of calculation for this system. Comparing the three ligands, it is clear that for N less than 3, formamide has a significantly greater binding energy, followed by methanol, and then water. However, as N increases, the difference becomes less pronounced, until at N equals 4, the trend flips, with water becoming slightly favored over the other ligands. This overall relationship has been explained by the polarizability of each ligand, which follows the same trend of water to methanol to formamide, and the cation-ligand charge transfer that occurs in the system. At increased coordination, steric interactions, as well as the decreased charge on the cation, decrease the attractiveness of an additional magnesium ligand bond. These results have general agreement with results from Peschke et al., which found that acetone follows the same trend. Finally, we move to mixed ligand complexes, both water-methanol and water-formamide. Some examples are shown here, with the 5-water-1-methanol and 5-water-1-formanide shown on the top, and the 3-water with 3 of each ligand shown on the bottom. Outlined in blue is the empirical expression proposed by Dudav and coworkers for predicting magnesium complexes containing formamide, methanol, and water in some combination. This predicts the total binding energy from single ligand incremental binding energies. The actual total binding energy is the sum of the incremental binding energies, assuming binding occurs in the order formamide, then methanol, then water. Results from this paper are shown on the right. This expression was based on the observation that the incremental binding for water decreased more when either methanol or formamide was already bound to magnesium, compared to water being bound initially. Evaluating this method at the B3LYP level, a mean absolute error of 3.06 kilocalories per mole was found across all possible complexes. A selection of 6 of these 30 structures are shown in the table, with the actual binding, empirical binding, and the difference shown in kilocalories per mole. Similarly, for the range-separated hybrid, a mean absolute error of 3.14 kilocalories per mole was found. This indicates that this empirical method is extensible. For the double hybrid, a mean absolute error of 2.83 kilocalories per mole was found, while for the coupled cluster, a value of 4.98 kilocalories per mole was produced. This indicates that the original expression is roughly extensible. However, moving up to the coupled clustered level of theory sees a notable increase in the error, although it is still fairly accurate. Given the roughly 50% increase in error for the coupled clustered method, and that Dudav's original equation exclusively overpredicted empirical energy minus actual energy, I decided to refit an equation of the same form. Using a non-least squares fitting on 10 of the 30 structures, this produced a mean absolute error of 3.25 kilocalories per mole, which better aligns with the results seen for the other 3 methods. Starred complexes in the table were included in the fitting of the data. From this study, we can take away that formamide and methanol bind more favorably at low coordination, while as the complex approaches a full shell, water becomes the favorable ligand. Looking at a simple method for modeling mixed ligand complexes, we found the expression from Dudav and coworkers remains reasonable at higher theory, though it can be more accurately fit. This indicates that the B3LYP level is fairly reliable in predicting the overall relationship between the single-type ligand incremental energies and the mixed complex ligands total binding energies. Potential continuations of this work could include looking at other ligands, including more complex options with multiple binding sites like carboxylates. A comparison between groups like methanol and formamide and the larger molecules such as some amino acids, which contain hydroxyl groups or amide groups, could be used to examine a relationship between the easy-to-model group and the more relevant or interesting large system. Though the ability of the empirical model to predict total energies is interesting, it's far less relevant today than when developed. Increased computing resources make it likely simple enough to calculate binding energies for mixed ligand complexes more accurately with DFT or a post-Hartree-Fock method. So the benefit of having a simple relation would be relegated to early stage predictions. Thank you for listening. I can now field any questions.